Welcome everyone to this course. In today's class we are going to discuss of high level synthesis of arrays. So, as you know, this high level synthesis is something which convert an high level behavior written in C or C++ into register transfer level design. So, we should understand how the important construct of a high level behavior like arrays gets mapped into hardware and what kind of bottleneck it might create during the efficient hardware generation. Okay. So, that would be the discussion topic today. So, as you know, this array is a contiguous memory location, right. So, if you write a 100 integer a 100, so it is basically 100 of integer in the memory, right. Now, if you think about how this array is going to map to hardware, so obviously you can map this array into registers. So, you need in that time 100. So, if I just write int a 100 and if I assuming int is 32 bits, basically it is 100 into 32 bits. So, this many register bits will be occupied, right, and since in a FPGA kind of Stargate the number of registers are limited or a fixed. So, mapping this array into register may not be a good idea, right, because then what is the solution? In the FPGA board we have also construct like RAM and ROM, right. So, which is something RAM is used where you want to read and write both, and ROM is only for read only memory, right. So, if you want to have some data which you want to only read, then you can actually store that things into ROM. And ROM and RAM is also the similar kind of thing, is a continuous memory location. So, it is a very one-to-one correspondence with the array, right, because the array is also is a continuous data and it is a continuous memory. You just map AI will be mapped to MI, right, as simple as that. So, that is the best target. So, we understand that mapping these arrays into RAM or ROM based on their access is the best way to do that. Okay. So, now we will see what is the bottleneck, right, what is the problem here. So, now the problem is in the RAM or ROM we have a fixed number of ports, right. So, the port is something read or write port, write port or both read write port, but we are going to discuss about the both read write port. Okay. So, for a block RAM, say I have taken an example of say size n and the width is m. So, it is n into m size RAM and it has a single port, right. So, each port has multiple inputs. So, for each port we have a address line, we have a data line, we have a write enable line, these are the inputs ports and we have a output line. So, these all four things combined to a single port, right. So, these are the component of a port. Okay. And how the read and write is going to happen into the memory. So, I am going to specify address I and say some data D and I will just put write enable equal to 1, right. So, if I just put write enable equal to 1, then what will happen? So, in this particular RAM, say this is memory and the ith location data D will be stored, right. And if I put 0, then it is basically read, right. So, then what will happen? Whatever the output, so out will be m of I, right, and this data is irrelevant in that case. So, this is how the RAM is get access in the hardware, that it has ports and you specify whether you want to read or write and you specify the address. If you want to read, you just make the write enable equal to 0, so that the content of that address will be come into the output, and if you want to write something there, you make the write enable equal to 1 and you specify the data you want to write, you give the address and in that particular location that corresponding data will be written. Okay. So, this is the overall idea. So, now the main bottleneck comes here because this particular RAM has fixed number of ports. Okay. Usually it is a single port or dual port, okay, RAM. So, that means if it is a dual port, that means at a time you can only write or read at most 2 times into the design, because there are 2 port, either you do 2 writes, 2 reads, 1 read, 1 write, whatever it is, but you can actually do 2 operations on the RAM, right, and it is a single port, you can only have a 1 access to the RAM and in a clock, okay. And that is create a problem, because once we write a C code, we never bother about how many array location is going to use into compute on one operation, right. Take a classic example. So, here I have written a dummy code function which is actually doing a summation for sum I, which is basically ai plus ai minus 1 plus ai minus 2 and ai minus 3. So, there are 4 array is going to add to sum I and the I is going from 3 to 20, right. So, this is what is happening. So, there are 4 array location is getting accessed, right. So, if I now think about I want to map this particular array A to a memory say block RAM M, then what is going to happen? There are 4 access to do one operations, right. So, in this once we write the C code, we never think about that, we just assume that this particular operations are going to happen in one clock, because this 4 data is getting accessed, but it is not the case in hardware. So, now think about a single port RAM. So, how many clocks you need to read this 4 data? You need 4 cycle, right. And then if the operations are like this, it is showing here there are 2 operations. So, if you assume that there is no operation chaining, so you need 2 clock to execute, right. So, 4 plus 2. So, that means 6 clocks you need just to do one iteration, and that this loop is happening for say 17 iterations, right. So, it is basically this number of iteration is going to happen to complete this loop, which is something 102, right. So, 102 cycles are needed just to execute this, but it is a dual port. So, you can actually access 2 data. So, I will access this 2 in clock 1, this into clock 2. So, I need 2 plus 2, which is 4 into 17, right, which is something 68 cycles. So, you can understand just having the port number of ports, you can see the difference in the performance, it will be much slower design, right. So, now obviously, this is something is a bottleneck, right. So, what is the way out? So, once we write a memory, I mean C code with array, we can clearly understand that we need to minimize the parallel access, right. So, somehow we have to write the code such a way that the array access is as minimized as possible, right. So, obviously, there are certain data you have to read, you cannot just stop reading the array, because you need the data, right. But we can clearly understand this access, unnecessary access will create a bottleneck for performance in the hardware, and hence we need to minimize this parallel access to the array. We will come into more detail, and how can you do that? Obviously, you can rewrite your code. I will give an example of the previous code in the next slide, that how can you rewrite your code just to minimize the number of memory access, or you use the high level synthesis tool features to do the same, right. So, in this particular lecture, we are going to discuss both. So, given an exam program, how I would just analyzing the array access, can I reduce the access? That is something we will see, and this is the same thing can be done using the high level synthesis tool features. So, both things we are going to see here, and the whole class I am going to do in a example base, right. So, because in a big example, if I take a very big case study, it is very difficult to convince. So, we will take a unit test case, and we will take a very unique scenario, and we will try to see how doing some kind of array manipulation helps in performance. Okay? That is how I am going to continue this discussion. So, the key idea is this. So, many times we will notice that this array access is something redundant. We unnecessarily access the same data multiple times. Instead of accessing the same data multiple times, let us read it once and store it in the hardware. What is the point of reading the same data multiple times in the array or the memory, because it is a bottleneck, performance bottleneck? Let us read it once and store it locally and reuse, right. So, the key point here, the whole discussion is you read the array minimum time, you store it locally, and then you reuse, right. So, that will reduce the memory access as much as possible. So, that is the overall key objective, right. So, now with this objective, let us look into this code, and let us see how can we rewrite this code just to reduce the memory access and hence improve the performance. Okay. So, if you just see when your I equal to 3, what is happening? I am going to access A3, A2, A1 and A0. I am just writing the index only. Okay. So, this is what I am accessing, right. So, this is when I equal to 3. What about the I equal to 4? When I equal to 4, what I am writing? So, since this is 4, this is 3, this is 2, this is 1. So, what I am going to access? I am going to access 4, 3, 2, 1. When I equal to 5, so this is basically A5, this is A4, this is A3, this is A2. So, what I am actually accessing? 5, 4, 3, 2. I hope you understand the pattern that I am trying to figure it out here. So, when I equal to 6, I am accessing the A6, A5, A4 and A3. So, what is happening here? Whenever I transit from the one iteration to the next iteration, only the value that I need is A4, new value, and the rest of the things is common, which is already available, that I have already read for my previous purposes, right. Once I move from I4 to I5, the next iteration, the only data that is not available with is A5, right, and rest of the data is already available. A4 to A3 2 is already available. So, no point reading A4, A3 and A2 again when I equal to 5, rather you use the data is already written in the previous iterations, and then you just only read this A5 in every iteration. So, with this idea we can actually understand that we can only read only one data per iteration. So, earlier it was 4 data, now it is only 1 data. So, obviously the cycle, if it is a single port, so earlier it was a 4 cycle, now it is a 1 cycle. So, it is a 3x improvement in only the reading part, right. So, it was basically so I do, even if it is a dual port RAM, so earlier it did 2 cycle, again I am need only 1 cycle because I am reading only 1 data for this. So, this is something the basic idea that you only read one memory location in every iteration and use the other 3 location which is already read and you reuse them. Okay. So, with this idea I can rewrite this code into this, right. So, which is very simple that, so I assume that A0, A1 and A2, because in the first iteration I need this A0, A1, A2. So, that is I will read before start of the loop, right. So, this will need 3 cycle, right. So, I will just store them into T0, T1 and T2, and in the loop what I am going to do, I am only going to read AI because that is the only new thing I need, A3, right. So, and then I am going to add this T0, T1, T2, T3. This is nothing but A3, A2, A1 and A0, right. And then what I am going to do? What I am going to do is I am going to move this because there are 3 temporary variables. So, initially it was to hold 2, 1 and 0, now it has to hold 3, 2 and 1. So, what I am going to do? I am going to move this 1 to this location, 2 to this location and 3 to this location, right. So, this is what I am doing. So, I am moving this T0 to T1, T2, T1 to T2 and T2 to T3, right. So, that means, so that it is in other way. So, T1 to T0, T2 to T1 and T3 to T2, right. So, now that means every iteration I have T0, T1 and T2 which is actually holding the value of. So, this is my T2, this is my T1 and this is my T0. So, every iteration T0 is already holding the value AI minus 3, T1 is holding the value AI minus 2 and T2 is actually holding the value AI minus 1. I am only reading this into T3, right, and then I am just moving the whole thing by 1, just shifting the things so that I am going to T3 can read the new data, right. So, this is how if I do, I can actually I just show that from 4 to 1, this is the 3x performance improvement I am going to get for this example. Okay. So, the key takeaway of this discussion is that sometime just looking into the array access, you see whether is there any duplicate reading is happening or the same data which is already read, I am going to read it again or not, multiple reading. So, the multiple reading can be avoided, right. So, the multiple reading of the same data will be avoided, and what we can do is we just store them locally and reuse them, and which is actually both the code is doing the same thing. So, but people will say what is the difference, they are doing the same thing, but this will is much better in terms of the hardware, because this is actually where the number of array access is less. So, the overall performance will be greatly improved if I just write this version of the code. Okay. Now, I will introduce another problem. Okay. So, this is one where we actually reducing the array reuse. Now, I am going to talk about the mapping, how this array gets mapped and where what is the problem it might happen and how can I actually make this mapping better. Okay. So, I am going to take 3 such problems and I am going to introduce a new concept. Okay. So, the first example that I have taken here is I have taken a very hypothetical C code. Let us say it has 2 array A1 and A2, which is an integer array which is of 1000 locations, it has 500 locations. Okay. And then in a loop what I am doing is I am just updating A1 with a value 1 AI and A2 with a value 2, because it has 5 locations I have a condition, right. So, basically in this loop I am going to write the A1, all the locations of A1 and all the locations of A2. Okay. So, and I am assuming the integer is 32 bits throughout the discussion. Okay. So, now say during the mapping it turns out to be that we have only one dual port RAM is available. Okay. So, that means I have a RAM which has 2 ports, I can read 2 data or read or write 2 datas from that RAM which is of size 2K, right, 2000 locations, and each of them is 32 bit width, right. So, I have a RAM which is one data is 32 bit width. So, this is 0, this is 31 and it has locations 0, 1, to 1999, right. So, there are 2000 locations and it has 2 ports, right. So, I can read 2 data. Okay. So, with this particular RAM I want to execute this particular behavior, because I have 2 arrays. In general I need 2 RAMs, right. This will be mapped to RAM 1, this is mapped to RAM 2, but I do not have 2 RAM available with me. I have only 1 RAM available with me, right. So, how can I execute this particular program using a single RAM, right. That is the question that I ask you. So, I will request you just think of, pause the video for a minute and then you move to the solution. Next slide. So, the solution here is that you have 2 array, but what we understood here that this array of size is 1000 and this is 500 and my RAM is much bigger, this is 2000 locations. So, if I map this array 1 into RAM 1, it has 1000 unused locations, right. Once you map that, it is unused, and if I map this array 2 into RAM 2, it has 1500 location is unused. What about, can we map both of them into a single RAM, right. So, basically the idea is that map both A1 and A2 into single RAM. So, if I do it like this, so that first 1000 location I just put A1 and the next 500 location I put A2, and so whenever, so basically A2 and this is my say A3 array. So, A3 I is equal to array I A1 I for I 0 to 999, right, and for I 1000 to 1499 A3 is nothing but, sorry, AI A3I is nothing but A2 I minus 1000, right. So, basically that I am actually mapping this A2 to the 1000 to 1499 those indices, right. So, if I can do that, then actually I am able to use the same RAM, right. So, which will actually solve my purpose, right, because it has lot of locations. So, I can just map them into one array, right. So, this is the solution. So, what we can do, I can rewrite this code like this. Instead of 2 arrays, I am going to use the same array, which is I just give an example in the previous, and for each iteration I am going to write AI equal to value 1, and since this array 2 is mapped to from the 1000 to 1500. So, for I am going to add I plus 1000, or I am going to store the value 2, right. So, this way I can actually able to execute this particular program into using a single block RAM, right, and you can actually do these things manually, because you understand that you from the hardware specification that you have a very big RAMs, no point having 2 array, which I can do using single array, and which will help me to map the whole thing into a single block RAM. Okay. So, this is what is called the array merge, right. So, the idea is that whenever there are many small arrays, if I just map this particular small arrays into individual block RAM, most of the locations of the block RAM will be unused. So, rather you merge this into a single array, and then this single array can be mapped to a single block RAM, which will reduce the number of block RAM uses. So, there is one bottleneck here obviously is that if you just map all this small array into a single block RAM and you want to access all of them at the same time, then again the problem that we discussed earlier will come, right. So, we try to identify the arrays which has access at the non overlapping time. That means, say this array 1 I am going to access in say time step 1 200 in this time, this I am going to access in say 200 to 300 this time, right, and this is going to access say basically from 300 to 400 this during that time. So, that means these arrays are actually getting accessed in different time, and hence they can be merged. But if the both array are accessing in the same loop, then it will reduce the number of access, and if some cases that might stop you to map the whole thing into a single block RAM, right. So, for example, here you can see here there are 2 access. So, if I map them into single array, now you have 2 access. So, if it is a dual port, there is no problem, because it is a dual port, so you can access 2 data. But if you map another array A3 into the same array A, then what is going to happen? Now we have 3 accesses, and since the dual port, the performance will be affected by that. So, we need to keep in mind that we try to identify the small arrays which are have non overlapping access, or they are accessing in different time, let them merge into one, and then that merged array can be mapped to block RAM. Okay. So, this is what is called merge horizontally, right. So, this is what is called merge horizontally, and if you do it a little bit formally, so suppose you have an array A1 which has m locations and A2 have n locations, and it is say 8 bit and this is 12 bit, okay, these two arrays. And then how the mapping is happening? So, I am going to map this A1 here, which is has 0 to m minus 1 location, and m2 n plus m minus 1 is my A2, right. So, that is where I am going to map this A2, and since this is basically say 12 bits and this is 8 bits. So, this part of the things is basically 0 padded, right. So, these are all 0, which is basically has no meaning, because this is 8 bits. So, these two array may not be of same data, may not be of same width, right. So, in that case the rest of the part will be automatically 0 padded, right. So, you do not have to bother about that, because you are not accessing that, because when this map happen, the tool will make sure that this particular location has zeros, okay. So, this is what array merge horizontally. And now you the tool, usually the high level synthesis tool have features to do that, you do not have to do yourself also, right. So, specifically because the tool that I am going to use in this particular course is Vivado HLS of Xilinx, it has a pragma. So, whenever you want to do something, you have to instruct the tool, right, you do something, and that is given by the pragma, right. And since this is a array mapping, the pragma name is HLS array map, right. It that means how do you going to map the array to RAM during high level synthesis, okay. And then how do you have to specify? You have to specify the array. So, array is given by variable. So, A1 I want to map into A3 and it is horizontally, right. So, basically you have to specify for each array. So, this is I want to map A1 to A3, A2 to A3, right. So, basically this is what exactly is A1 and A2, and this is my A3, exactly the example that I have shown here. So, if I just write these two line of code in your program, it will actually automatically do this job for you, right, or you can actually do yourself by rewriting the code the way I have shown here. So, both are same thing. So, writing the code yourself has more control, and here if you ask the tool, it may or may not do based on the situation, right, or it might give you the warning that it is not possible to do it. So, both can be used, okay. So, I will now introduce another problem, okay. So, again you take the same example that I have taken for my previous problem 1, that I have two arrays A1 and A2, I am going to access both in a loop, in a single iteration of the loop, okay. Earlier I told you there is a dual port RAM of size 2K. So, since this is a 1000 location is 500, so both can be merged horizontally into the same array, because it has enough locations, right, it has 2000 locations and I need 1500 locations. So, I can map them, and it was a dual port, and hence even if I map both of them into the same RAM, I can access two data in the same iteration, because I need to access both of them. So, everything was solved with my merge horizontally things. Here I am going to introduce another problem. So, I have the same behavior, but I have now a single RAM, okay. First of all, it is a one RAM and it is a single port, it does not have two ports. So, that means even if you merge this into horizontally, your two access won't be satisfied, because it has a single port, okay. So, you have a single RAM, it has a single port, right. So, it has a single port, not like earlier there are dual ports, and it has size 1K, right. So, this is 0, this is 1 to 999. So, it has 999 locations, but the width is 0 to 70. Earlier it was 32 bits, now it is 70 bits, okay. So, that merge horizontally won't work primary of two reasons. The first is it has only 1000 locations, and if you try to merge them horizontally, you need 1500 locations. So, merging horizontally is not possible. And also the another bottleneck is that it is a single port, and you need to access two times in a single iteration. So, that is also not possible if you just merge horizontally. So, can you still execute this particular program using the given block RAM? Okay, that was the question. Again you think yourself, pause it here and then move to the next slide for discussion. Okay. So, the solution here we have to be understood that we have 1000 locations. So, hence you cannot merge horizontally obviously, but the things given here is that this 70 bits. So, I have lot of width in this direction, right. So, I need the integer which is 32 bits, but I have 70 bits. So, if I just map A1 to this here, so if say I map A1 here, so it will use 0 to 31. So, 32 to 70 that will be unused, right. So, that is also unused bits. What about mapping A2 here? So, this was my A1 and this is A2. So, I am actually mapping both A1 and A2 vertically. Okay. What does it mean? So, I am now accessing, this is my say array A, AI, which is will give you both A1I and A2I, right. So, accessing just one location of this array will give the data both A1 and A2I. So, just because, and this is 32 to 63. So, this part is again 0 padded, right. So, that is what is called vertically. If you have the RAM is lot of width in the data width of the array RAM is more, then I can actually instead of merging horizontally, I can actually map the array vertically as well, right. So, that is what is exactly discussed here, that A1 is stored 0 to 31 and then A2 is stored from 32 to 63, and this is my because A1 of size 1000 and this is 500. So, this is what, and this all part is 0 padded. Okay. And how I am going to access? So, whenever I am going to access the memory location I 0 to 31, those bits is nothing but AI, and 32 to 63 bits are nothing but A2. Okay. So, this is what is called merge array vertically. So, when there is no enough room to merge horizontally, you look for is there any space vertically, and then you can merge vertically. Again this diagram the same thing, that you have there are two array, you merge vertically and one location specify two array locations. Okay. So, again in the high level synthesis, so the same thing if you just try to define the things formally, if A1 of size m, A2 of size n, and then what I am going to do, I am going to put a 0 to m, 0 to m, that is my first location, and then m plus 1 to m plus n minus 1 is the second location of the array of AI. Okay. And then and the whatever the things are not used, it is basically 0 padded. Okay. And I can access by just doing this, right. By just doing this I can access the same location. Incidentally, the tool like Vivado HLS has the facility to do the things automatically as well. If you just specify again the pragma, that I want to instruct the tool to do something, I want to instruct the tool to do this array mapping of variable A1 to A3 vertically, array mapping of variable A2 to A3 vertically. So, this is where exactly the thing is going to do is it will put A1 here and A2 here, and if the width is not enough, it will give a warning that it is not possible to merge, because I do not have any RAM which has enough width to map vertically, right. Otherwise, it will just do this exactly the things that I have discussed in the previous slide. Okay. Now, I will move on to the problem 3. So, another scenario I am going to introduce, okay, and I am going to see what could be the solution. Okay. So, let us take another new example where you have array A and B, both of 1000 size, 1K size, and I am actually accessing Bi equal to Ai plus A2. So, what is important here? I am accessing a B one time and A two times in an iteration, right. For each I am going to access A 2 times, B 1 times. Okay. And what is given to me? I have given 2 single port block RAM. Okay. So, I have given 2 block RAM of size 1K. So, that means A and B can fit in there. Okay. I have 1K size, but the size width is 70 bits. Okay. And this is 32 bits, right. So, these are all 32 bits, this is 70 bits. Okay. So, this is what is given to me, that this is 0 to 69, this is 0 to 69, and the location is basically 0 to 999, and the locations are from 0 to 999. Okay. So, obviously, you can think what is the problem, I just map A here, B here, right. Obviously, because the size matching width matching. So, there are a lot of unused bits for each width, but the requirement is that I want to read all the data of one iteration in one cycle. Okay. So, if the requirement is this, obviously, there is no problem in mapping here. So, there are 2 arrays, 2 block RAM, size is same, both has single port. So, it has a single port, this also has a single port, it does not matter, because so for B it does not matter because we have only one access, but for A that single port matters because it has 2 access in one iteration, but I want to access both of them in single cycle, right. So, that was the problem, that for B there is no problem, it is perfectly mapping to a block RAM, it has one access, single port. So, the one cycle requirement of reading is done, but for A it has, since the block RAM has single port and this particular array has two access in a iteration. So, I cannot just read both AI and AI plus 500 in single cycle using the single port. Okay. So, can I still map this program into these two array available to solve this to meet my requirement. Okay. So, again you think on this and pause here and you see the solution next. So, the solution here is yes, it is possible because I have lot of width available in A, right, as it is basically the merge vertically thing, but since A is already of size fixed. So, what I am going to do, I am going to break A 0 to 500 this location into A1, and so this is 499 to be precise, and this is 500 to 999 this location into A2, right. So, basically I am folding the A into two arrays. Okay. Once you have these two array, I can merge vertically because this is 32 bits, this is 70 bits, right. So, that the way I fold it, so that whenever I access this memory, this is say my memory 2, so which is memory 2I, I am actually accessing A1I, basically I am accessing AI and AI 500, right, because the single access of this memory, because I am mapping this A1 here and A2 here, whenever I am going to access a single location, I am accessing both I and I 500, and that is what is my requirement. Okay. So, this is exactly the solution that I talked about, that I fold this A into 2 and I will store only in for the 500 locations, and the first 0 to 31 is my A and this is A plus 500, right. So, I plus 500. Okay. And so, whenever I access MI, which is basically 0 to 31 is A1 and 32 to 63 is my AI plus 500. So, I can actually do the things. So, this kind of specification is not possible by high level synthesis tool like Vivado. So, if you see that you are actually taking lot of time, you want to improve the performance of this kind of array accesses and still you want to map them into a single block RAM, you have to rewrite your code in this manner. So, that once you rewrite this code, the tool will map this particular A into a block RAM, and see, although it has a single port, still can execute the things in single cycle. Okay, all the access in single cycle. Okay. So, I have already discussed 3 scenarios where we actually have to merge the arrays, because to utilize the array better or the memory better, right. So, either you merge horizontally or you merge vertically, but both will give you the lot of performance benefit. Okay. Now, I will just talk about the reverse side, that sometime you probably have to partition the array as well. Okay. So, what is the scenario where you have to partition the array? Is basically if you have a very large array and your RAM size is smaller, right. For example, if you say array of 10k size and your block RAM is only 5k. So, you cannot map this 10k into a block RAM because it has a lot of double size. Okay. So, if it is the case, what the tool usually do, it put all this data into register, and you can understand that it will create 10,000 into 32 number of bits of registers, which is huge. It might occupy all registers of the FPGA board. Okay. So, whenever you have a very big array, you have to be very careful about mapping them into block RAM. Mapping them into block RAM is kind of must for very large arrays. Okay. And sometime if the array size is too big, that cannot be fit into a single RAM, then the best idea is just partition into smaller arrays, so that each small array can be mapped to a different block RAM, right. So, that is the idea. And how you should partition? The partition should be such a way that the access is distributed, right. So, if the locations here and the locations here should be accessed in parallel, but the locations of here should not be accessed in parallel, then they have to access in the same clock, and that will create a bottleneck, right. So, when you try to partition the array, it is not that you split it here, there will be many ways you can split it, I am going to discuss it here, but the splitting should be very such a way that the accesses of different components should be in parallel and the access of the content of the same array should be sequential. So, that the bottleneck of the port should be avoided. Okay. So, that is what the idea. Okay. So, again you can do this using the array partitioning, you can do it manually or you can do using the Pragma HLS partition, HLS array partition. You mention the array name, you do the what type of partition you want to do, I am going to discuss those. What is the factor, how many small part you want to make break the array and which dimension you want to break, right. So, I am going to discuss them. Okay. So, the array variable name is the array name. So, you mention the array which is the big array you want to partition. Okay. So, now based on the access pattern of the array, you have to decide whether what is your partition type. Okay. So, there are three partition type. One is cyclic, right. So, if the array is say A1 to say 1000, so in 1000, so in cyclic and say suppose you want to break into 4th component. So, what I am going to do, I am going to put A0 in the block 1, right. So, you want to partition into 4, right. So, I just put in A1, I will put A0 and then say in A2, I am going to put A1 because it is a cyclic manner, right. It is not something in the A3 component I am going to put A2 and A4 component I am going to put A3, right. And then cyclic way I am going to do A4 here, A8 here, right, A8 here, 5, 6, 7 here, 8, 9, 10, 11 here, 12 here, 13, 14, 15. So, this is how I am going to cyclic way I just break it. So, if the access is such that you are actually accessing A0 and A1 at the same time, A4 and A5 in the same time and so on, probably it is better idea that you put A0, A4 into one block and A1, A5, A13 those things in another block and so on. So, that even if you want to access A0 and A1 in the same time, this can be accessed from two different location of block RAM, so that they can be parallelized. Okay. So, this is when the cyclic is important and the block is something is obviously you understand that suppose I want to partition the A, again the same example says 1 to 1000, there are 1000 location. So, in A1 I am going to put A0 to say A1 to A250 say, okay, and say I want to partition into 4, right. So, in partition 4 I want to put A250 to 500, you understand the point, right. So, the first part you want to put in array 1, A3 I am going to put A500 1 to A750 and A4 I am going to put A751 to 1000, right. So, this is how I can actually split. So, I just give the first part into block 1, second part into second part say block 2 and so on. This is block and if you mention complete, it will split into registers, right. So, in some cases say there is the way you are accessing, even if you partition it does not solve your purpose. So, then you can actually split the things into individual registers, okay. And it is actually useful the complete if it is very small array, no point actually mapping them into block RAM, because a block RAM size is minimum is say 500 and this array is A10, A12, no point holding a 500 location for 10 datas, right, rather you split it. So, that time you again do partitioning and you mention this is a complete partitioning, that means this array will be distributed into registers. So, that is also where this array partitioning will help. So, the exactly diagram that I try to show. So, if you have these locations, so block will put 0 to n minus here, n minus 2 here and so on, and cyclic I am just 0, 1, 2, 3 and so on, right. I am showing 2 partition here and complete into individual registers. Okay. So, what is the factor? So, how many component you want to create? So, here your factor is 2, the example I have taken the factor was 4. So, how many small partition you want to create, that will be given by the factor. Okay. And the dimension is also important whenever there are multi-dimension array, right. So, there are say A2, A6. So, it is a 2-dimension array. So, which dimension you want to partition? You want to partition this dimension or this dimension? So, that is something you have to decide and that is given by the dimension. Okay. So, if you say I want to partition the dimension 3 for this array, so the dimension 3 means it will, so this is my dimension 3, this is 2, this is 1, right. And then what will happen, it will create and say I want to do a 4, factor is 4. So, then what is going to happen? So, I am going to create 4 such array, right. So, the third dimension will create each partition, okay. And similarly, if I try to put the dimension 1 you do not have to mention the factor, because if you just mention I want to break the dimension 1, then what it will create 10 such partition, right, each of them of size 6 into 4, right. So, this is how I am going to partition, and if you just make the partition dimension 0, it will make into register, right. So, it will partition into individual array. So, one important thing here is that if you just mention I want to partition the dimension 1 and I want to make a factor equal to not 10, rather say it is 2, right. So, that means what is going to happen, this dimension 1 will be split into 2 arrays. So, that time I will create 2 array A1 which will be of size 5, 6 and 4, and another dimension which is basically again of size 5, 6 and 4, right. So, mentioning both, if you do not mention factor, it will split the whole dimension into individually, or if you mention the factor plus dimension, then it will split that particular dimension based on the factor. So, since here I mentioned the factor equal to 2 and the dimension size is 10, so it will split into 2 part, right. So, this is how it will create the things. Okay. So, I hope you understand, and again this is something based on the application. So, suppose you have written a code and you are seeing that because of this array it is you want to map this array to a particular block RAM, and it is getting split into register, and as a result you are saying that your area is not sufficient to map, right, and you identify that because of a block big RAM big array is getting mapped to register, the problem is happening. So, what you can do is you just partition the based on that particular array, just by you running one, you analyzing the fact, you understand that and you actually partition the things, and then after partitioning probably those small arrays will be mapped to block RAM, and hence your performance will be achieved, or you are able to map the whole thing into a target architecture, right. So, these are all advanced level of things, but once you are actually becoming master of high level synthesis, you need to apply this kind of techniques to achieve your target. Okay. So, just to summarize before conclusion, that in this discussion we have seen that how the array is getting mapped to hardware, it is basically mapped to block RAMs or ROMs, and we have seen that since the array that block RAM has a limited access, so it is better to reduce the parallel access as much as possible, and whenever you have the content which is getting multiple time read, we are accessing the same data multiple times, instead of reading it memory multiple times, it is better to read it once, store locally and reuse, right. So, that was the idea, and for bigger arrays you probably have to partition them into smaller arrays to fit into a target block RAM, or if you have a smaller arrays, it is better to merge them into together, so that the utilization of the block RAM will be much better. Okay. So, that these are the things, tricks you have to taken care during efficient synthesis of array into hardware. Okay. Thank you.